These are your Integrated Math 2 Section 3.1.1 notes. 3 for Module 3, Topic 1, Lesson 1. Our learning target is I can investigate absolute value functions. That includes graphing the function, writing equations for the function, identifying transformations given a graph or an equation, and analyzing word problems. The topic is functions derived from linear relationships for Topic 1. So get this down in the notes, pause the video, and we'll go to the first example. All right, first thing is the parent function, or the most basic function for an absolute value is y equals absolute value of x. That's equation notation, or function notation, f of x equals absolute value of x. Now, I'd like you to have these formats down. We'll be talking about this, but y equals a times the absolute value of x minus c plus d. Or you have f of x equals a times the absolute value of x minus c plus d. We will be talking about what the a value, how does it affect our graph, how does the c value affect the graph, how does the d value affect the graph in terms of transformations. But for now, let's just graph the basic parent graph, which is, let's just do a little xy table. All right, so start with if x is 0. If x is 0, y is 0. Okay? If I substitute 1 for x, I'm going to get 1. All right, so you get 1, 1. If I substitute 2 for x, I substitute 2 for x, my board messed up on me there. 2 for x, then I'm going to get 2, 2. So 2 and 2. If I plug in -1, I'm going to get +1. So I substitute x as -1, but I get +1. If I substitute x as -2, then I get +2. So as we saw in classroom, we get a v here. So I'm just going to finish it off. We could just do the full table of values. I'm going to graph it here, and this is my parent graph here. It is a v for a linear absolute value function. All right? So again, get that down. Go to the next example. So now, let's look at these two. Now we're going to change. We're going to add more to it. We're going to go, all right, y equals 2 times the absolute value of x minus 3 plus 1. All right, so in this case, we have some we have the a value. A value is 2. The c value, be careful. The format is x minus c. So when you see x minus 3, that means c is actually +3. It's a subtraction sign here. So that's a +3. So c equals 3. If we got x plus 3, if it was x plus 3, well, that would have been x minus -3. So we would know that c is actually a negative value, which is why this would be a plus sign. All right? So it's always going to be the opposite sign of what you see here. And then the d value is the +1. All right, so in class we've looked at transformations. And what we know is how this affects the parent graph is the a value is 2. If it's bigger than 1, we know it's a vertical stretch. And that changes all my y values. So when we went over before, we had 0, 0. Then we went over 1, we went up 1. We went over 2, we went up 2. Well, now with the value 2 here, that changes all my y's. So when I go over 1, I'm going to go up 2, not 1. And I'm going to go over 1 again, I'm going to go up 2. Over 1, up 2. Doing that both ways. So that's how the a value is going to stretch it. If this a value is between 0 and 1, like this one, like a half, then it's going to compress the graph. It's going to make it a fatter v. All right? What does this do here? The c value is 3. That means this is going to move 3 to the right. And the d value is 1. It means it's going to move it up 1. So if we go back and look at our original parent graph, what I know is this graph is going to go 3 to the right. It's going to go up 1. But then it's going to stretch. So again, instead of going over 1 up 1, it's going to go over 1 up 2. Instead of going over 2 up 2, it's going to go over 2 up 4. So we're going to take this graph, we're going to transform it. So let's do it. I know I'm going to go from 0, 0 is my vertex. I'm going to go over 3 to the right, up 1. There's my new vertex. Now, I'm going to use my stretch factor of 2. So I'm going to go over 1, up 2. Over 1, up 2, just like slope, right? I'm going to go over 1, up 2, over 1, up 2. Here's my new graph. Now, could I also just do a table of values? Absolutely. Okay, and if I was going to do a table of values, the great place to start here, if you do a little XY table, great place to start would be get this to be 0 inside the absolute value bars. So what value of x would make it 0 inside the absolute value bars? That's right, 3. So I would find if x is 3. Boop. Substitute x is 3 in here. You get 3 minus 3 is 0. 2 times 0 is 0. 0 plus 1 is 1. Okay, so when x is 3, y is 1. Oh, look at that. 3, 1. There it is. Then I probably would have tried, okay, how about 4? Substitute 4 in here. 4 minus 3 is 1. Absolute value of 1 is 1. 1 times 2 is 2. 2 plus 1 is 3. Oh, look at that. There it is. Okay. How about if we want to try just x is 1? If x is 1, substitute it in. 1 minus 3 is negative 2. Absolute value of negative 2 is 2. 2 times 2 is 4. 4 plus 1 is 5. Look at that. It'd be negative 1 comma 5. Isn't that our point we have here? Yes, it is. Okay? So the idea is you could do a table of values or you can use the transformations to graph. Let's do another one over here. So this one, what's my a value? A value is equal to negative 0.5. All right, what do we learn in class when it's negative? The a value is negative. It's a reflection over a horizontal line. We typically say it's a reflection over the x-axis, but it does depend when I do my transformations. It could have been a transformation over the line y equals 4 as well. But for this case, I'm going to say we transformed it as a reflection over the x-axis. All right? And the 0.5 means that absolute value is between 0 and 1. If that a value is between 0 and 1, we know it's going to be a compression. It's going to make that a fatter v, if you will. Okay? Then the c value, it says x plus 2. Well, remember it's x minus c. So isn't that x minus negative 2, which becomes x plus 2? So therefore our c value is actually negative 2. And then our d value is 4. So again, thinking back to the original parent graph, what's going to happen here? Well, we know that c is negative 2, so it's going to go left 2. The d value is 4. It's going to go up 4. So this vertex is going to go left 2, up 4. It'll be right there. Okay? But we also know it's a reflection over the x-axis. So we know it's going to be opening down. All right, so let's do it. We're going to go left 2, 1, 2, 3, 4. We know it opens down. If it was a reflection of the parent graph, it would just go, we'd go over 1, down 1, right? Over 1, down 1. But this time, our a value is actually only a half, or 0.5. So I'm going to go over 1, down a half. Over 1, down a half. I just keep doing that until I run out of space. Okay, I got to do it the other way as well. So it's over 1 this way, down a half, down a half, down a half, down a half. All right, and there's my v. Only this part shows on my graph, but obviously I can keep going and make it look nice and pretty. All right, again, could I have done a table of values? Absolutely. If I was going to do a table of values, I would have started with what value of x? That's right, I would have started with negative 2. Right? If x is negative 2, I get 0 in here. Okay, absolute value is 0, 0 times negative 0.5 is 0 plus 4. I get negative 2, 4. Oh, look at that. Negative 2, 1, 2, 3, 4. Okay? If I substitute it in, let's just try 0. Substitute 0, I get 2. Absolute value of 2 is 2. 2 times negative 0.5, negative 1. Negative 1 plus 4 is 3. Oh, 0, 3. There it is. You want to plug in 6. We substitute 6 for x. 6 plus 2 is 8. Absolute value of 8 is 8. 8 times negative 0.5 is negative 4. Oh, negative 4 plus 4 is 0. So when x is 6, we get y is 0. Oh, look at that. There it is. Okay, so you can learn how to graph in this class right now. I'm happy if you can graph with a table of values. If you can learn how to graph using the transformations, that would be great as well. And obviously, we're going to be using the technology and Desmos to graph as well. But I'd like you to have the basic skills of graphing by hand in this class. All right, now let's go another way. Let's say we're given some absolute value graphs, linear absolute value graphs. Can we write the equation for them using this? So first thing you should look at is where's the vertex at? Vertex here is at negative 1, comma 2. So does that give us any information up here? Sure it does. It tells us the c value is negative 1. It tells us the d value, it transformed up to, so d equals 2. And the a value, how can we figure that out? Let's see. It goes over 1, up 1, over 1, up 1. Isn't that just like the parent graph? So that means the a value is actually just 1. So name that function. Write equation notation here. Let's go y equals absolute value of x minus negative 1. So we're going to say plus 1 and then plus 2. Oh, remember from your IM1 days, they asked you for domain and range. Well, we know that domain is going to be x equals all real numbers, so it goes on forever, right? Includes all the x values. But the range would be the y's, and the range would be y is greater than or equal to 2. All right, let's look at another example. This one, where's my vertex at? It's at the point negative 3, negative 2. All right, so what's my c value? That's right, c value is going to be negative 3 on this one. So c equals negative 3. What's my d value? Goes down to. So d is equal to negative 2. And then, was there a reflection? There was a reflection. And is the a value still 1 though? See, over 1, down 1, over 1, down 1, yeah. So the a value is still 1, but it's going to be negative 1 because of the reflection. So it's going to be a equals negative 1. All right, name that function. Let's go y equals negative sign like that, or you can say negative 1. I kind of like to say negative 1 like that. And then absolute value of x minus negative 3. So it's going to be x plus 3. And then it's minus 2. All right, one more for fun. This one, let's see here. The vertex is now at 2, 3. All right, so my c value, the original function shifted 2 to the right. So we know that c equals 2. My b value is up 3, or my d value, I should say, I said b. D, as in dinosaur, is going to be positive 2. And then my a value, well, we know it's going to be a negative value because there's reflection. And let's see, is it still 1? Over 1, I go down 2. Over 1, down 2. So my a value is negative 2. All right, name that function. Function is going to be y equals negative 2 times the absolute value of x minus 2. And then it's going to be, uh-oh, you see my mistake I made? Hope you caught my mistake. D is 3 here. Sorry. D is 3, right? So plus 3. Sorry about that. All right, so there's our function. Now, range on this one I forgot to talk about. The range is going to be the y's. So it's simply y is less than or equal to -2. The range on this one is y is less than or equal to 3. The domain for an absolute value function will always be x equals all real numbers, unless you have a real life scenario where we have some type of domain restriction. Okay? All right. One more. Let's do analyze a problem here. So we have a snack company is filling bags with pita chips sold by weight. Each bag should contain 8 ounces of chips. The specifications allow for a difference of 0.25 ounces. The function f of x equals the absolute value of x minus 8 represents the difference between the weight of a bag of chips and the specifications. Okay? Graph the function. What weights meet the specifications? All right. So we want to graph this. Well, the weight in ounces is x. So what would make this 0 in here? Would be 8. So if I'm at 8 ounces, that's the perfect bag of chips, right? There's no difference in the weight. This is going to be our difference in the weight from 8 ounces. All right. Well, if I go over 1 ounce, so I go to 9 ounces in my bag, then I'm going to have a difference of weight of 1. So I'm going to go up here to 1. But wait a minute. If I go to 7 ounces, aren't I also only one ounce off? Yeah. I guess if I'm the customer, I'd prefer to be the 1 ounce over. But, you know, considering my weight, I probably should be the one that's 1 ounce less. But that's a different story. All right. So then we want 10. That's 2 ounces above the 8. So that's going to be 2 ounces. That's going to be to the top of my chart. And then I would like to go to 2 below, and that's going to go to the top of my chart here to graph it. Okay, this is going to be a little hard to do, but I'll try my best. Not the best graph. It's supposed to be a V. This is pretty ugly, sorry. And we're supposed to have a V there if I did a better job. So then, but here's the problem. You can only be off by 0.25 ounces. The company wants to stay in business. They want to be giving way too much. They also don't want to short their customers, have the customers unhappy with them. So they only give you 0.25. So it's going up by 0.1s. So this would be like 0.25 right here. So we go straight across here. And then we'd have to read what our ounces would be. Well, we know that basically it can be 8 plus 0.25, and all the way it can be 8 minus 0.25, which would be like 7.75. So the bag of chips is going to have to be between 7.75 ounces and 8.25 ounces. All right? And that's it. So you get different types of problems like this where you use the graph, interpret the scenario, and you answer the questions. All right? So that's it for your 3.1.1 notes. Thank you.